Okay. So first thing, side correction, this is not a talk about IJC. That comes later this afternoon. This is a talk about software development for chemistry applications. It's a talk for geeks, really. Apologies to the chemists. The basic premise is how to be able to make ChemAxon-based or more generally chemistry-based applications easier. How to make the development of those applications easier and faster. And these are the people who have been mostly involved with this. The first three come from Argentina and the fourth from Australia. So it's a pretty multinational project, this one. The aim was to investigate how we can basically make web-based applications for chemistry, and how we can use the best-of-breed frameworks that are often used in the IT sector, and are not commonly used within for chemistry applications. And these frameworks basically do the heavy lifting for you. So you have to write much less code because the framework does the work for you. And the framework, by using these frameworks, it gives you the chance to really get real code reuse rather than copy and paste code, which very often we tend to use nowadays. And the other real benefit of using a framework is that we can insulate ourselves from the implementation details. And the benefit, as I see here, would be that we can avoid the need for, in our case, specialist JChem developer skills. And any person who is familiar with developing web-based applications or even non-web-based applications should be able to create a chemistry-based application. They wouldn't need to understand all the inner details of how JChem works to be able to create that sort of application. So let's look at an example of how things work typically today. Here is the JSP example that I'm sure you've all seen. Just this point here. And we've got, on this screen, we've got the sketcher, where we draw our molecule, and over here on the right, we've got a large number of structure search options that need to be specified. And this page really shows the best and the worst of the breed. The sketcher is put together here typically with a bit of JavaScript code. And this is really nice. The JavaScript provides an API to how the sketcher should appear and behave in the browser. Really, all you have to do is copy and paste this bit of code, reparameterize it, and it'll work in your application. And when the underlying implementation details of the sketcher change, the API provided by the JavaScript will be updated in the ChemAxon library, and everything will still work. And that happened quite recently. It happened, was it 6 months ago or so, in one of the Marvin upgrades. And if you were using this approach, everything worked. If you weren't using it, you had to go in and change your code because of those underlying changes. So this is really quite a nice example of how you could encapsulate the implementation details to some extent. This bit over here on the right is really pretty ugly. This is the JSP page, or a tiny fragment of the JSP page. And you can see it looks, it looks like a JSP page. It looks really, really ugly. We're mixing up database access code, presentation code, and everything here. And this is hundreds of lines of code to get this. And if you then wanted to do another application that had the same sort of options, you'd have to copy and paste the whole code. And it gets ugly. It's not nice. The second example is if you're looking at the DAO level. So this is how you might persist a structure in the database. In this case, we're updating the structure. This is the method call for updating the structure. And I'm not going to go into this in detail. Obviously, it's Java code. But people who've written this code will recognize that there's a gotcha on pretty well every line in this code. You've got to know what you're doing. There are things here that will come and kick you in the painful bits if you're not careful. We don't really want to be having to write this sort of level of code in order to get our application working. We also don't want to have that level of knowledge to be able to write those applications. So there are various problems here. Firstly, we have to write tons and tons of code. Secondly, we do need specialist knowledge. We've got to understand how Marvin works. We've got to understand how JChem works to be able to write these applications. And there are lots of traps. If you don't do it right, you will be caught. Because we're writing lots of code, we've got to do lots of testing. but we probably don't do lots of testing. So we have a hole there. Also, it's difficult to test this code. It's not easy to rigorously unit test this sort of approach. And when that application needs to change or migrate, it's difficult to refactor and upgrade. It's a major task to have to deal with those sorts of things. This generally results in the fact that we're using copy and paste coding rather than getting real code reuse. And another problem here is we're strongly coupled to the underlying chemistry engine. In our case, it's probably JChem. But if we wanted to change JChem, even from JChemBase to JChem Cartridge, it would be quite a lot of refactoring to have to do that sort of change. And to change it from a JChemBase system to a Symix-based system, or preferably the other way around, it would be a huge amount of work. So let's take a step back. Let's look at how Java web-based systems have evolved over time. Originally, the first way of doing things really was when JDBC and JSP started to be available. That was very early in the days of Java. Tend to be used in an approach that is called the sort of the Model 1 architecture. And the JSP example is a sort of classic example of this. Basically, it ends up in code mess. You can write applications, but very quickly they get unmaintainable, and you end up in a mess. Quite quickly, people realized that they were getting into a mess, and something called Model 2, also known as Web Model View Controller, came along, exemplified initially by the struts framework. That improved the architecture significantly, but it still was far from ideal. There was suddenly configuration hell. You had to write so much XML file, a lot of duplication of stuff. It wasn't really as productive as it should have been. Over time, the Model 2 architecture has improved. There are new frameworks such as Stripes or Spring Model View Controller that make use of sort of improvements that have happened, typically convention over configuration, which means just put things in the right place and they just work. You don't have to configure it, it just works because you're using the right convention. And DRY, which stands for don't repeat yourself. So configure everything once, not multiple times. So that has provided a lot of improvements over time, but there are still some limitations in these sort of frameworks. And then finally, more recently, there have been some more object-oriented frameworks available. Google Web Toolkit and Wicket are good examples here. These are more object-oriented in nature and provide some further improvements, like improved refactoring support and basically a generally more object-oriented approach. But the world outside Java was also doing things, not surprisingly. And probably about, what was it, about four years ago or so, Ruby and Rails really started to become very prominent. And it really set the new standard. Ruby on Rails was a complete application stack that handled your complete application all the way from the database tier up to the presentation tier. It made extensive use of convention over configuration and DRY, and it was, because of the nature of the Ruby language, it was a lot more productive environment. You could create an application much faster than you could using older approaches like what is being used in the Java world. And Ruby on Rails really took off and became very successful. Other sort of older and more conventional languages, such as Python and PHP, well, they may be a bit old, and they may be not so fashionable nowadays, but they were certainly still doing things, and there are frameworks for those that, again, have followed many of these principles as well. And importantly, there's now some newer frameworks that are appearing to run on the Java virtual machine that I think are particularly interesting to look at. Most notably, Groovy and Grails, and Scala and Lift. So these are new languages that run on the Java virtual machine. They are very strongly aligned with Java, and they really complement Java very well, and so hence they complement the nature of the ChemAxon tools very well, but they are a lot more productive. So what we wanted to do is to look at various of these things and see how we could use them in chemistry. One thing, as I'm sure all developers will be aware, there's a huge amount of choice out there. There's a huge amount of frameworks that people could use for pretty well everything. In whatever category, XML, web frameworks, web components, Ajax, persistence, there's a huge list. This is just a tiny fraction. Can be very confusing. Choosing which frameworks to use it's a very arbitrary decision because there are so many of them, and it's difficult to make a subjective decision on this. We're not saying we've chosen the best frameworks. We've just chosen ones that seem to work well and seem to have the right criteria for us. So let's take a step back. Let's think about a standard system. This might be a system we're building for a business unit, not a chemistry-based system. These sort of systems generally have very simple data. They handle things like bank accounts, purchase orders, catalogue items, addresses, airline flights, things like that. They're simple numeric and text data, and they're relatively easy to handle. And for these sort of applications, the persistence tier, this is how the data is saved into the database, how it's read from the database, how it's queried. This has been largely automated using persistence frameworks or object relational mapping tools. And they handle all the database operations. And really, if you were building one of these standard systems nowadays, you wouldn't even consider doing that sort of persistence yourself. You'd almost certainly use one of these persistence frameworks, such as Hibernate, to do that for you and to make your life a lot simpler. But chemistry software looks to me to be stuck. It's not really benefiting from these recent developments. It tends to be what I say lovingly handwritten. We write the low-level code ourselves and we love it, but it takes us a lot of time to do it and has all of these drawbacks that I mentioned earlier. And this results in poor productivity. And why is this? Why doesn't chemistry do it the right way? Why do we have to do it in this painful manner? And can we solve the problems? So that's really the scenario that we started to look at. And what we did is really an experiment. We said, okay, it shouldn't be like this. Let's see how we can do it, see how we can improve things. So it was an experiment. Can these problems be solved? And so we have to ask, why is chemistry difficult? Why can't we just treat molecules like a purchase order? And the reason for this is the molecules are very complex. The CRUD operations, this is the persistence operations in the database, the create, retrieve, update, and delete operations, and most importantly, the query cannot be expressed as simple SQL statements because molecules are complex. When we search in molecules, we need to handle chemical fingerprints. We have to handle things like that. We can't just do that as a simple SQL statement. And basically, we need a chemistry engine to help. Now, our chemistry engine is JChem. And these chemistry, in this context, we're talking about Marvin and JChem systems, but the same really would apply to whichever chemistry engine you're using. They're typically mostly JDBC or JSP based, or maybe using some of these frameworks such as struts in a more limited manner. They tend to be handwritten. They don't tend to use some of these more modern frameworks. In my experience, they tend to use copy and paste code with all the disadvantages of that, and they make very little use of components and reuse of components. And the result is they're difficult to understand, they're difficult to upgrade, they're difficult to refactor, they're difficult to test. But does it have to be this way? Well, that's what we wanted to investigate. So we wanted to look at, are there benefits in using languages other than Java? Can persistence frameworks be used with JChem? Can we benefit from modern web frameworks? And can we get real code reuse? And can we get real database and chemistry engine independence? So can we just switch out JChem and put in its place JChem Cartridge? Can we switch out the Accord cartridge and put in place the JChem cartridge with minimal changes to our application code? So the aim was really to exemplify building a chemistry system using some of these best-of-breed tools. This is the application we built. It's not designed to be a very sophisticated application. It was a proof of principle just to show that we could build this sort of application with these frameworks. It's a very simple web-based application. We import a number of vendor catalogs into a simple database, relational database model. There's a structure table, there's a sample table, so each structure has a number of samples, and each sample comes from a particular source. The source would be the supplier. So it's a very simple application. It's not supposed to be rocket science in terms of an application. It's also not supposed to be sophisticated. It's not the ultimate in sort of user experience. What we're trying to do is sort out the technology side of things. And what we built looked like this from the architecture point of view. The different tiers of the application, but more importantly here on the right, the database we're using, we could just plug in Oracle, MySQL, or Derby, probably other databases as well. The persistence framework we used was Hibernate, and the web framework we used was Wicket. The Hibernate was obviously using JChem to do the structure persistence, and Wicket was obviously using Marvin to do the structure display. So the ideal situation would be that the structures don't get in the way. And we can look at this really for those other tables, the source and the sample table, because these are just plain data tables. And to exemplify this, I've got a sort of a pseudocode here for if we'd written this application using Groovy and Grails. And these were the domain objects for the source class and for the sample class. And this is all the information, this is all the code you have to write. You define the properties, you define the relationship between the source table and the sample table, and then you can just write code that runs a query. Sample, find by code, and it looks up that code. This method in the Grails framework is automatically generated for you. I haven't written that method. It's generated dynamically in runtime based on the convention that you're using, find by code. And it looks up the fact that find by means I want to do a search. Code, well, let's see if I've got a field called code. Oh, I have, therefore I'll run that as a query. To delete that sample, you just do sample.delete. So in an ideal world, you end up with code like this, which is really, really simple to write, really, really simple to use. But that doesn't handle the structure tables. For structures, we've got a problem because we're using JChemBase. And JChemBase is necessary because we want to be able to search. We can't get rid of it, otherwise we wouldn't be able to search for our structures. And this is a screenshot of the architecture for JChemBase for how it works in a sort of a browser-based environment. But the issue is that we must use the JChem API. That involves using some classes which will be familiar with developers: connection handler, update handler, JChem search. So we have to pass our queries through the JChem API, but we also need to use plain SQL. So we need to generate SQL because these become filters on the JChem search. Also, if we're doing things like creating tables, then we need to go through the JChem API. Again, we can't do that purely with SQL. And so it's not obviously suited to the SQL generation framework such as Hibernate or JPA. Can we solve that problem though? Well, let's look at Cartridge, in fact, before we do that. Cartridge is a bit easier because we've got function calls here that basically encapsulate the JChem engine. So everything can be done with SQL, and that's the real beauty of the Cartridge. The issue is that it's not standard SQL. We've got these JChem operators, JC formula, JC compare, JC evaluate, and things like that. So this is non-standard SQL. But we can basically customize our SQL generator in our Hibernate tier to generate this sort of SQL for us. So with Cartridge, it is a bit easier. Now, if we were now extending our Groovy and Grails application now to include a structure table that was using the JChem Cartridge, it looks a bit like this. Quite similar to what we saw before. We see the fields, the structure field, the mol formula, and the mol weight field. We just have to use a little trick here to say that the molecular formula is a formula, which is the JC formula structure. And what this then does is when the SQL is generated, it uses that formula to retrieve the value for formula and molecular weight. So it's only a very slight change to the basic scenario. So for Cartridge, we can solve this pretty nicely. It doesn't actually solve query. We still have to do a bit more work to be able to query this data, but we can use named queries, which lets you specify the query at the SQL level. And because with the Cartridge, we can do everything with plain SQL, that provides a perfectly satisfactory solution for most cases. The problem with Cartridge, though, of course, is it's only suitable if you're running Oracle, and it's only suitable if you're running the Cartridge in Oracle. So can we have a more generic solution here? Well, so basically we're asking, can JChemBase be tamed so that it can work with Hibernate or JPA? And if we do this, can the developer work with this in a way that's agnostic to the chemistry engine being used? So can we just switch out one chemistry engine and put in another chemistry engine, and none of our application code needs to change? So how we do this, and this is the real geek section here for the next minute or two. We're doing this using the Hibernate event model. This is the Java doc for this particular package. And there are a whole lot of listeners that you can attach to Hibernate, which basically you can use to intercept the calls to Hibernate. So either before or after Hibernate does something, you can put on an interceptor and hook in your own code there. There are a whole list of these, which basically lets you hook things up to when structures are inserted, deleted, updated, or whatever, and you can hook in your own code to customize how that is going to happen. And so what we do is we created something which we call the chemistry engine and the bridge. So what happens is at the persistence level, the user, let's say, wants to persist a structure in the database. So they've got a new structure and they want to save that into the database as a new row. The Hibernate framework, or in this case, is the JPA framework. We hook in to these events through the engine, through a bridge. So the bridge is notified that Hibernate is wanting to persist a structure. Then that engine bridge then passes on to the engine implementation and says a structure is wants to be updated or inserted, and then the engine implementation persists that structure in the way that is appropriate for that particular engine. So in our case, using the JChemBase API. To see this slightly more in action, again, very schematically, though. So we're persisting a structure here. This is at the sort of the Hibernate level. So we're just saying entity manager persist this structure. So we're trying to save that structure into the database. The pre-insert event listener picks this up. So this is the listener that lets you hook in code before the structure would be inserted into the database table. The bridge calls its onPreInsert method, and then passes that on to the particular engine that's being used. And the engine says create structure. Create structure uses the JChemBase API, in this case update handler, to insert the structure into the JChem table. And when that's done, the control is passed back to the Hibernate layer that basically saves it and would commit the transaction. That would then commit the SQL for the other data into the database. And so engine bridge looks a bit like this. We just have these interceptor calls for onPreInsert, onPreUpdate, onPostDelete, and onPostLoad. And this just passes each of those on to the particular engine implementation. And this is what the engine looks like. In this case, this is the JChemBase engine. We have a method called create structure that basically just delegates to this do create structure method. And this code looks almost identical to the code that we saw earlier, because we're using the JChem API to persist it. But the difference here is that this code is now in the library. This is the user, the developer is not having to write this code. All they're having to do is work at the persistence framework level. So this implementation detail is completely hidden to the developer, and a different engine would do the persistence in a completely different manner. And so this is our structure entity. In this case, we're doing it in Java, not in Groovy. We got fields for molecular weight, for formula, for getting the samples and things like that. It looks a fairly standard entity. We can also define, in this case, the standardizer, so that when the table is created, we get the right standardization rules. And most of the things are configured with annotations. So we're defining what the structure table is called and things like that, and parameters for whether the stereo, how the stereo is handled and things like that. And this is really the important bit. All the rest is the geeky implementation details. This is what the developer would actually need to do to actually use this. We've got a method, let's say, in our service tier, and we want to create a structure. Well, all we do is we call entity manager persist for that structure. When we want to look up a structure based on its ID, the developer, the only code they have to write is entity manager find. So the developer now is working in this completely agnostic manner, not needing to know what the underlying implementation details are. And to prove this, one of the aspects obviously is the plugability. Hibernate isolates you from the underlying database. So you write the same Hibernate code. It doesn't matter whether you're using a MySQL database or an Oracle database. Hibernate handles the translation for you. But our chemistry engine now also isolates you from the underlying chemistry implementation. So we can now swap in and swap out our engines. So this is the only configuration change you need to make to change from using JChemBase to using JChem Cartridge. You just change the name, the class name of the chemistry engine in this particular configuration file, and that just one line of code, you've switched from using JChemBase to using JChem Cartridge. Query is a bit more complex. I've got a very simplified representation of this here, and I don't really have time to go into it in detail. It's a bit, we've had to do a bit more work here to enable query to work. It's not trivial because of the way we have to pass the query through the JChemBase API, but also use SQL generation to generate a SQL filter that is passed onto the JChem API. But the implementation basically deals with that. The query, we have an object-oriented representation of the query that you sketch in the browser. That then gets inspected and translated into a form that can be executed by the particular engine. The result you get back is a hit list of the IDs. It's not fully loaded entities, which would be a performance bottleneck. So you just get a list of your hits, and then you can go back to the database to retrieve the real data, the structures or whatever for those particular lists. So there isn't really time here to go into query in detail, but the engine implementation does support querying as well as the basic persistent stuff. Another aspect of this is, I said we were using the Wicket framework for doing the presentation tier, presentation of the service tier here. And just to illustrate the benefit of using these sort of frameworks, let's say we wanted to expose certain parts of this application as a web service. Well, this is the entire code that's needed to do this. Firstly, you have to enable RESTful web services at the servlet level. This is what the configuration change you need to make in the servlet container, Tomcat or whatever configuration file, basically just to enable the web services. To expose the functionality in our service tier, this is a method in our service tier. We just have to provide the right annotations that basically enable the web service. And then to use it, here's a bit of Groovy code that we're actually just calling the web service. That's the URL. Web service get, I can't see the details there, but anyway, and print out each structure we've got back. So web services, we don't have to develop web services. All we've got to do is turn them on, really, which makes a huge difference. So, Doug, have I got time to do a quick demo, or should I? Okay. So just to show that this isn't all smoke and mirrors, there is something behind it, some real code that runs. This is the application. Let me just check that. Yeah, I am still connected. So we've got a very basic way of browsing through the structures. We can select a structure here and see which vendors it's available from. Most importantly, we want to be able to search. So we go to the search tab. Here you get what would be fairly familiar to people. We can specify the search type. We can enter in our substructure. And then run it, and we get our search results back. So all of this is going through this, these frameworks I've described. The persistence is done by Hibernate. The implementation here is JChemBase engine. The database that is being searched in this case is I think it's a Derby database. But all of those things are pluggable and switch outable. As I said, it's not designed to be a sophisticated application. It's just a proof of principle that the technology does work and is usable. Also, I should add that there's Wicket components here for encapsulating the sketcher and for the options. So these components now can just be reused in other applications. We don't have to copy and paste the whole ugly code that we saw before. This is just a component that you can include in your web page, and all of the options will then reappear in your next application. So, yeah. In summary, did we succeed? Well, from the persistence point of view, yes, I think we pretty clearly did succeed here. The approach seems to be successful. We've created a meaningful but relatively simple web application that uses these JPA interfaces in a very clean manner. So any developer who is familiar with using Hibernate or JPA could develop this sort of application, and they wouldn't need to understand anything about JChem and anything about Marvin. We've given ourselves some vendor agnosticity. Is that really a word? At least that we can switch between JChemBase and JChem Cartridge. We haven't yet tried switching between other vendors' engines. That's going to be more difficult, I think, but it should be possible. And that's talking about the engine is pluggable. In the web tier, we haven't really done anywhere near as much. So most of the work of the experiments we've done is at the persistence tier. The web tier is relatively limited. We've got a small number of Wicket components, like the one for the sketcher and the one for the search options. The reason why we haven't done so much here is because there are so many web frameworks that we don't really know whether we're using the right one. I mean, we like Wicket, but you might not. And each company is probably going to have their own favorite framework to use, and so it's probably not worth our while investing a lot of work in any particular web framework here, unless there is some sort of consensus that is the one to use across many of you. So the components that we're generating, some of this is relatively short term, some of it's more medium term. The engine architecture and their implementations, at least the JChemBase and the JChem Cartridge implementation, those are developed. We're also generating a Groovy library that basically encapsulates JChem. So if you're using Groovy, and I really do, for any Java developer who hasn't yet looked at Groovy, I really do recommend you do. It complements Java really, really nicely. In terms of web components, we could produce components for any number of frameworks. Standard JSP tags, the GSPs for the Groovy and Grails framework, Wicket, whatever. We don't really know what the demand would be here, which frameworks people really want to use. If you've got any particular suggestions or comments in this area, we'd certainly like to see them. So the components that we could create and have, at least for Wicket, are the sketcher component, one's for displaying structures, so the table component that displayed the search results, and the search options. Probably a few more we could create there as well, and we're open to suggestions for what might be useful. So what will be available? Well, firstly, I should say these are experimental tools. They're not ready for a production environment yet. We need to do more work to make them solid and usable in a production environment, and we'd certainly be interested to find out whether you think that is something we should be doing. We plan to use those maybe for creating internal systems and maybe for consultancy projects as time goes on. And the components may become available as an extension to JChem if there's demand. So in a way quite similar to how web services is provided at the moment as an extension to JChem, we might provide these frameworks as an extension to JChem as well for customers wanting to use this sort of thing. And we're certainly actively looking for people who have experiences here, because I know some people have started to look at these sorts of things as well. I'd certainly welcome any showing of any experiences that people have had in this area, and we're welcome to hear from people who might be interested in taking this sort of approach and using these things. So that's it. Thank you for your time. And have we got time for questions?
Yes, we do.
Okay.
First of all, thank you. That's a great talk. And we have a question.
So for the structure annotations, it looked like you had the table type annotation. So is that some more classes you added to be able to create the JChem tables?
You're meaning this slide, where we have annotations up here that basically specify the name of the table. This is the JChem table that is being created. And we've got an annotation here for the type of table. In this case, we're using a molecules table, but we could specify Marcouche or a reactions table. So yes, we've got part of the framework handles the DDL aspects of this. So you can, like Hibernate could create the tables for you. It's no good if it only creates the non-structure tables for you. So we've hooked in here as well, so that it reads these annotations and then creates the JChemBase table with those particular attributes of the right table type, the right standardizer configuration, the right stereo options, and things like that. So you start with an empty database, and Hibernate will create all of those tables for you.
Cool. And with the connection stuff where you integrated, just to confirm, because the slide was kind of quick, the connection that was being passed in, that was from, that was the active connection with the open transaction, right? So
yes.
like rollbacks and everything would be...
Yeah, that's the connection obtained from the Hibernate session. So it's done within the same transaction that Hibernate is managing.